Hello everyone, welcome to the Geoecolologist. I'm Dr. Krishnanand and you have been watching my videos on physical geography, evolution of geographical thought and other segments of geography as well. So in today's session, we are going to learn about a very interesting topic that is part of the core geomorphology that we study, and it is important from civil services point of view as well. So it is called channel morphology. So we have already studied about fluvial landforms, various kinds of processes associated to it and characteristics of those landforms. But in today's session, specifically in terms of the channel, in terms of the river morphology, its cross profile, its long profile and associated dynamics and geometry, we are going to study in details. So before we go ahead, please like and subscribe to our channel and don't forget to share the videos with others as well. So now let's learn about this channel morphology topic. So what is this channel morphology all about? Or it is also referred to as river channel morphology. So the word channel basically coming from this Latin word canalis or Old French channel, which basically means a pipe or a groove or a channel, which is basically a path. So we have already learned in the fluvial process, in the fluvial geomorphology, in the fluvial landforms, the role of these channels in shaping the surface of the earth. So that is important here. But here what are we learning is the morphology of this channel itself. It means the features that are related to this channel, right from river source to this river mouth. What does this channel look like? What are the important components of this channel? And how does this morphology, that is about the shape, the study of shape of this channel. So right in this longitudinal section as well as this cross section. So when we say this longitudinal profile of the river or the cross profile, we basically means along the river, that is longitudinal in nature, and across it, that is the cross profile. So we will learn about all those important shapes related to the features that are there in the long profile of the river as well as the cross profile of the river, and associated important things related to their fluid dynamics, their geometry. That is where morphology, that is where the shape is important in this channel morphology. So let's go ahead and learn furthermore. So what we see here is that channel morphology is also called river channel morphology, and it is a complete study of the channel from geography aspect to channel fluid dynamics aspect as well. So if you see this adjoining sketch or this diagram, if you see flow diagram, so what you observe, there are several factors that are important in a landscape as variable factors. So what are those important variables? If you see here, it is written independent variables. It means they are independent. So for example, geology, climate and human beings. Now these are three independent variables, but remember there are dependent variables as well. So those variables that are dependent upon these three variables, for example, sediment supply, stream discharge, vegetation, all these factors are dependent upon the independent factors like geology, climate, human beings action. So what happens when we talk about river channel morphology or simply channel morphology, these variables are important. So basically when we say that these are the dependent variables, it means they are bound to change, they are bound to have dynamism in them. So that is important that we learn. So these dependent channel variables are what? Width of the channel, depth, bed slope, grain size, bed forms, sinuosity. All these factors that we study are part of those variables which are determined by the previous variables, which are largely of the landscape part, which is geology, climate, human beings, and further those dependent variables as you see here like sediments, stream discharge, vegetation. So these are all interconnected in this entire fluvial geomorphology that we study. So for simplicity, what you use this word is streams. So these streams or stream morphology that we study, remember these are basically the flowing water. So that is what we study in fluvial geomorphology process. So for example, creeks, brooks, tributaries, river, it has several names and it also varies in scale from small scale to large scale. So that is important here. Now, why is it important? It is important because it provides an overview of the key factors determining the shape, that is the study of morph. So morphology of the entire watershed streams. So variety is there. Why different kinds of stream have different kinds of nature, its various shapes. So what is the reason behind it? That is what we discuss when we talk about river morphology or channel morphology. So the morphology of this river channel includes these four important things. What are these four things? as we talked in the earlier diagram, cross-sectional shape, its size, then its longitudinal profile, and also the planform pattern. Remember these four factors. These are resultant of these two important variables as we see. So largely what we see is that we have already studied these under denudational processes. Remember weathering, erosion, mass wasting, transportation, deposition, all these things. So these four factors governing the shape or the morphology are whose function? The function of these denudational processes. As these processes vary, accordingly the shape of the channel also varies, the size also varies, the profile also varies. So if you look into this image, what do you observe? This stream is here going from this end. Remember, this is what is it doing? It is meandering, and there's this section that is across the stream. This is called a cross section profile, and along this is called a long profile. But what you observe is there are several features and various shapes associated to this stream. What you see here: natural levee, back basin, then you have inactive point bar, active point bar, oxbow lakes, all these features that we study related to the streams. How these features are made in the longitudinal profile of the river or in the cross profile of the river, it is important to understand the role of these denudational processes. So if you want to remember channel morphology, now this is the way. Remember these three important factors: number one, number two, number three. These are not the factors. Basically what these are the components of channel morphology. Many places you will find that these components have been divided into 5 components. So what I did was I just made it into 3 major components. One is the channel geometry, the other is fluid dynamics, the last part is the hydraulic geometry. Now many places these types and patterns are separated and channel bed topography is separated from it, so it becomes 5 types. So these 3 components are what we need to learn when we want to discuss about channel morphology. So the first part you see here is channel geometry. So what does it include? Length, width, bend, slope, Thalweg, perimeter. Remember, these are part of these geometrical measurements, geometrical shapes. And where is it coming from? Now you have to remember the geographical thought portion. Remember Nile Delta and Nile based research in the Greco-Roman time. So because Nile river is a long river and it has a great morphology that was studied right from the source of the river to the mouth that is near the delta. So that is where this entire channel geometry and morphology study comes from. Apart from that, now this is the second component. So it is about the fluid, the flow part, the dynamics of the flow. So in flow, what do we observe? What do we measure? The discharge capacity, the velocity, the energy, the load capacity, the transportation capacity. So remember, it's mostly about the capacity, the capability, the velocity, the energy. All these factors are part of the dynamics of the fluid. And third component is what we see is the hydraulic geometry. So it is basically related to what? The hydrosphere specifically. So the water component, its types, its patterns. So what are the various types of the channels? What is its geometry like? Then how is this channel bed? So basically this bed on which this channel is there, its bed, how does it look like? What are the important components of it? So largely these are the 3 components. This is channel geometry, fluid dynamics and hydraulic geometry. Now let's one by one discuss about each of them. So first factor, what you see here is channel geometry. So as we know the components of it, the channel length, width, channel bends, slope, Thalwegs, wetted perimeter. Now every term is very simple, you can understand. The length is as simple, right from the source to the mouth. This is what is the channel length, right? Width is from this point to this point, that is the cross-sectional. So we understand. Bend, we already understand these kind of bends. We have already studied the meandering part. Slope, we already have studied in the fluvial cycle or the normal cycle of erosion, in the Penck cycle. So we already understand about the slope, high degree of slope, low degree of slope, right? In the youth stage, in the mature stage. So these things are there. But what is new in this is this Thalweg and wetted perimeter that is new in the entire series of geomorphology that we have learned. So what is this Thalweg? Remember, this is a German word. Basically, it means path along bottom of a valley. So this is what we say is the Thalweg. Now to simplify this Thalweg, there is an interesting way to understand. What is that way? Remember, this entire channel has a given width and a given length. But is it possible that the entire time this channel occupies the entire surface from one end to the end? remember it has a lean season and it also has a flood season. So what happens? Even in the lean season or in the flood season, there is a point, a particular path which is of the greatest depth, which always has water. So remember that path which is part of that segment or that journey, that channel journey, which always has water because it is the deepest part. So that is what we understand as channel thalweg. So thalweg is what? It is basically the deepest section of that valley which always will carry the water. So many people also explain this thalweg as that suppose if there is a fish, so what path would that fish take to cover this entire length of the channel? Remember, a fish would require more water, rather than it will not float or it will not move in the scanty areas. So it will like to have more water. So fish journey would be part of this deepest section of this entire channel, and this is what we understand as the thalweg. So these are those points which are the deepest in the channel. So they are joined together along the longitudinal flow of the river. That is what we understand as channel thalweg. And the word here in wetted perimeter. So what you observe in this diagram, if you see, this is what is the bed width. This is the maximum depth, as we see. Maximum depth we understood as area which is part of this thalweg. So if this point is the maximum depth, so we can observe from this bank to this particular point, this is the maximum depth part. And what is this perimeter? Remember, this is that perimeter which is wetted. It means this is that maximum extent which is always wet, or it is wet during even flooding as well. So that maximum extent till which this river wets its sides, its surfaces along it, that is called the wetted perimeter. So the cross-sectional area of the stream is determined by multiplying channel depth by channel width. This is very simple. So this is the depth and this is the width. And if you multiply width with depth, you will get what? You will get the cross-sectional area. So this is what the cross-sectional area of a channel looks like. But if we want to calculate wetted perimeter, so how will we do it? Remember, taking this assumption as it has been discussed, that if this is a general rectangular perimeter of a channel, so what will happen? In a rectangle, this part is the width part, and these are the two important major components as well, which are the sides. These are the two depths that are important as dimensions, which have to be multiplied with the base. So we have 2d. This 2d is coming from 1 and 2. And then where is this w? You remember, this is the width. So we have width plus 2d. That is what we understand as a perimeter. Perimeter is about what? The complete measurement of all the sides. So that is what we talk about, the wetted perimeter. Now coming to the second segment, that is after this we have fluid dynamics. So first we learned about the geometry part of the channel. Now we learn about the fluid dynamics. And under fluid dynamics, remember, all those capacity, energy, all those things are important. So let's begin with learning this channel discharge capacity. Now what is this discharge all about and how can we measure it? Remember, it is all about measurement. When we say, it is about quantification as well. So when we study hydraulic geometry, when we study fluid dynamics, when we study this channel morphology, lots of things have been quantified. So remember how to calculate this discharge. This is the formula where Q is for discharge, and then we have W, D and V. So W is channel width, obviously, D is the average channel depth, and then V is the average velocity. Now here it is not simply channel depth or velocity, it is average. It means at different points in this river, we take that depth and we measure the average depth. Similarly, in the center, it is more fluid, it is more mobile, it has more velocity, and at the periphery, the channel does not have that much of velocity. So average velocity will be calculated. So remember, it says WdV is the calculation of this Q. So Q is the discharge capacity. The rate at which water is transported by a canal is called discharge, and maximum discharge that any canal can transport is its capacity. So that is as simple as it, that maximum capability of a channel to transport a particular discharge, that is its capacity. So that is called canal capacity or channel capacity. And hydrograph is a graphical way of portraying this change in discharge over time. So if you observe this graph, this is a hydrograph. So this is discharge and this is time. So stream discharge or channel discharge, it is called, is basically what? The volume of water passing through a particular cross section in a unit time. So remember, if this is a stream and this is that cross section, so remember how much of material in that water passes through this cross section in given particular time. So it is measured in units like cubic meters per second, cubic feet per second. So per second, how much is the discharge through this cross section? That is the basic idea of this measurement of channel discharge capacity. And also along with it, there is something called base flow. What is this base flow? The discharge of perennially flowing stream is provided by influx of groundwater in the channel. So this influx provides what is called the base flow of the stream. So remember, for a stream which is perennial in nature, it's not that just the water is coming from outside through rainfall or glacial melting. Water is also coming from this base, coming from inside, right? That is important. So it is underground water coming up. So that is where it is important that this is called the base flow. This addition to this influx coming from the within, from the base, this is also known as base flow. Now the second part is about this velocity of this channel, which is called flow velocity. So what this flow velocity is? Basically, again, through this cross section area, at what speed is it flowing in that particular direction? That is what we measure as the flow velocity. So flow velocity is directly related to hydraulic radius, that is the cross-sectional area divided by wetted perimeter. Velocity of this channel is directly related to what and inversely related to what? So remember, it is now here to catch that when we say that cross-sectional area and wetted perimeter, how they are related to the velocity? When we say direct relationship. So what is directly related? The cross-sectional area divided by the wetted perimeter as we calculate the hydraulic radius of the channel. And inversely related is its roughness, because remember it is rough, so it will try to stop it. So that is where the friction comes into the picture. So that is inversely related to the velocity of that channel. Furthermore, we have already learned about this Thalweg. So more specifically, the highest velocity of the flow is where? At stream Thalweg. Remember this portion where it is the deepest, it is having the Thalweg. So this particular line is where you have the maximum velocity, and as you go to this periphery, you have the less velocity. Now along with it, something more is important to remember is this flow regimes, how these flow happen. So under very low velocity, now remember we have learnt about channel velocity. So there are two cases, either it is low velocity and it is high velocity in the other case. So during low velocity, water flows through this stream as smooth sheets running parallel to the bed. So remember, it is very low when there is scanty water, and it is very slow. So low velocity, it flows almost parallel to this bed, and that kind of flow is called laminar flow. So remember lamination just over the sheet, that is where it is laminar flow. And when it is fast, so the word itself is turbulent. So it is having turbulence in that. So it goes constant variation in the speed and direction of the flow. That's why it is called turbulent flow. So remember, turbulent flow and laminar flow are two kinds of flows that are involved in terms of the velocities of various kinds of streams. Apart from that, there is another important term that is important in terms of question can be asked. So Reynolds number, remember he was Osborne Reynolds, he tried to quantify this. This Reynolds number helps to predict the flow pattern. So simply through this number. So that is which is Reynolds number. This is here Re, and these factors are what? Density of the fluid, flow speed, then linear dimension characteristic, then dynamic viscosity of the fluid, and kinetic viscosity of the fluid. So these are various parameters that are important, which are physical parameters, which was used to actually calculate this Reynolds number. But for general understanding, if this Reynolds number is low, it means basically what? When it is low in number, it is laminar or sheet flow. When it is high in number, it is turbulent flow. So Reynolds number has direct relation with the laminar flow or the turbulent flow, that you have to remember. The next part of this dynamic is stream energy. So velocity is equally important as energy is important. So what happens? Remember, if the channel has lots of sediments and its velocity is less, if this is the case, what will happen? All the sediments will just stop there. It will not go further. So it is important that to transport that material which stream erodes, the speed, the velocity part of that stream in that direction is important, and that can be only effective when the stream energy is high. So that is why it is important as part of the fluid dynamics. Then the other part is sedimentary load capacity. So remember, this is that amount, that capacity of a particular stream or a river to carry that sediment load. So these are three types of loads that a river carries. So dissolved load, which is dissolved in the water. Then it can be a suspended load. Remember the process of suspension, when there is particles in the suspended manner, and then there is a bed load. So if that load is along the bed, so either it can be dissolved in the water itself, it can be suspended, or it can be a bed load. So these are the three types of capacity which is part of this fluid dynamics. Then we have the transportation capacity, which is equally linked to the stream energy, flow velocity. Remember, this is important. So what happens, this is the capacity of a stream to transport that material which it is carrying. When the greater transportation happens, when the energy is high, when the velocity is high, and what is important here, that if transportation capacity is less, it means the river cannot transport much of the material from the source to the mouth. So now the last component is the hydraulic geometry part. So earlier we understood the channel geometry. Now let's understand hydraulic geometry part, of which first is the channel types and pattern. So remember, on the basis of these geomaterials, these rocks, that is the soil rocks, which is important, the channels may be alluvial in nature, or it may have the bedrock. So channels may be flowing on the alluvial material or on the bedrock. So one is soft, one is hard. So remember, this is one kind of classification. The other kind of channel is like effluent channel and influent channel. So if there is more humidity, remember, there is constant water source. So perennial river are there, where in the humid tropics, and those channels are called effluent, E-F-F-L-U-E-N-T. So effluent is when you have lots of water coming in, lots of humidity is there. But if it is an arid or semi-arid area, so it basically means seasonal characteristic, so which is called influent. It is just seasonally present. It is only influential in a given time period. So this is another classification of the channel types. Now let's understand further types and patterns in an elaborated manner. The first part, alluvial channel, basically can be divided into 5 types on the basis of this sediment load, as we have understood, and also on the basis of this important factor which is called sinuosity. So let's understand first this sinuosity, as we understood the sediment load. What is this sinuosity all about? Now look into this particular image. If you can see, what is this? This is the entire actual length of the channel from point A to B, where channel is actually bending, right? So this is the actual length. But when we measure this length on a map in 2 dimensions, what do? We simply measure point A to point B. This is the aerial distance, the straight line distance. So what happens? One is the straight line distance between one point to the other point, and one is the actual distance. So what is the sinuosity? It is the ratio of these two, the length of the stream channel by the length of the straight line of that channel. So that is what this sinuosity basically simply means. So sediment load and sinuosity are 2 factors on which the alluvial channels have been divided into 5 types. So one is called suspended load channel. Name itself suggests it has lots of suspended load. Then it has mixed load, which is part of the sinuous thalwegs and small coarse sediments. So if the thalwegs are sinuous in nature, so that is where the coarse sediments are there. So coarseness is also important, where you have mixed load channel. Then suspended load channels, where high sinuosity is there. So if this ratio is more, it basically means that this numerator is more. That is the basic idea. So if this numerator part, that is the actual length of the channel, is greater, it means its sinuosity would be greater. Then further, meander braided transition. The name itself says it is meandering and braiding at the same time with larger sediment load. And the 5th type is the bed load channel, where there is lots of bed load condition. So it is highly unstable in nature. Now, according to Leopold and Wollman, 1957, river channels are divided into these 3 types as well. This is another classification. So one kind of channel is called straight channel, and this straight channel calculation, or sinuous channel calculation, or meandering channel calculation, how do we do it? it has been suggested by Leopold and Wollman through this formula. It has been quantified. So remember, this quantitative formula is to actually calculate something which is called sinuosity index, which is called SI, sinuosity index. Now sinuosity index is a parameter to actually divide channels on the basis of how straight it is. Is it actually very straight? Is it curved? Is it meandering? So remember, straight channels value less than 1.05 when we measure SI, that is sinuosity index. Sinuous channels measure between 1.05 to 1.5, and meandering channel has the greatest sinuosity index, that is more than 1.5. So this is one thing that we need to remember when we say that any river is meandering. No, not all river curves are meanders. It will always depend upon this sinuosity index. How do we actually classify them, as meandering river or just sinuosity channels or sinuous channels or straight channels? So when we say channel patterns, now these are various patterns of those types only. So let's understand these patterns. So one is straight channel, sinuous channel, meandering channel, braided channel. Then something new what is here is this term, anastomosing channel. And apart from this anastomosing channel, there is something which is also important we are going to learn in the next slide. So remember these names, and further what we have in this table, you can pause the video and you can watch it here. What are the other important parameters here? It's morphology, that is its shape here. It's sinuosity index that we already know. Then it's load type, its erosive behavior, and its depositional behavior, and its width depth ratio. So these are the factors on which we have either straight pattern or sinuous pattern or meandering pattern or this kind of braided pattern or anastomosing pattern. So these are important patterns, and apart from that, these 5 patterns, there is this 6th pattern which is important, that is called Anibranch channels. This is also important because this is based on the branching of the channels. So one is called braided channels. So what is the difference? In a braided channel, this braiding index is important and it is highly dynamic. So when we say braided channel, it keeps on braiding and changing its course dynamically. But when we say Anibranch channels or Anibranches, remember it is same kind of situation. There is a branching in the river, but the difference is that these channels typically cut into this floodplain, dividing into different large number of channels and creating islands in between. So this is largely of a fixed nature in comparison to the braided channel. So we need to understand this braiding index as well. So J.C. Bryce in 1964 gave this braiding index, which is basically calculated like 2 into sum of the length of island or bars by division this length of the reach. So this is how we calculate the braiding index. And the second part that we need to understand is the bedrock channels. So its types and patterns. So basically bedrock channel is of a fixed nature largely, which has structural control that is important. And when we say structural control, what is that? It is basically what? It is having joints, bedding planes, underlying geological strata is important, which controls the river morphology. So river cuts through, but the control is not of the river. It is controlled by the landscape. So that is important here when we talk about bedrock channels. So you look at this particular pattern, what do you observe here? There is a creation of this gorge and canyon situation. This is of Grand Canyon, as we know. But remember, the structure is important here. These joints, faults, these things are important. And in this case, river occupies path of the least resistance. Where it is least resisted, that is where it is moving. So that is important when we talk about bedrock channels. Then further, what we have to study is the last segment, which we know as channel bed topography. So what is the channel bed like? So if this is the channel, what is this bed like? Does it have these depressions or coarser areas? So what is it like? So in this, few important things we have already studied, that is like sandbars, sand dunes, potholes, plunge pools, that is in the longitudinal course of the river, in the fluvial geomorphology, in the landforms we have studied. So there are 2 things that we need to remember. One is called pool and the other is called riffle. So what is this riffle and what is this pool? Now if you can look into this structure, this cross-sectional profile of a pool and river. Now remember, a pool is having greater depth, and a riffle is not having that kind of greater depth, but largely this width. So one thing that is important is about the depth parameter. The other part is about the undercutting. So pools are more easily seen in meandering stream, where outer edge of each meander loop is deep and undercut. So it is actually in the thalweg area, remember, pool part. But riffle is basically a shallow water zone which is largely of straight nature. If you observe this particular cross-section profile, which is wider outreach, so this is part of the cross section where you have these riffles and you have certain pool. So pool is deeper and riffle is actually broader and shallower in nature and coarser in nature. That is important here in channel bed topography. And at last, what we need to learn in channel morphology is this concept of graded stream. So this graded stream concept, which was actually well discussed by A. Cyril and G.K. Gilbert in their work, was furthermore discussed by Mackin in 1948. So a stream equilibrium concept. Now remember, there is a balance in the stream flow as well, which is called stream equilibrium, and that is where this kind of stream is known as graded stream. A stream that attains this profile of equilibrium, which is equipoised in nature. But what is this equilibrium about? Now look into this image, you can understand. This is one stream and this is the other stream. In one stream, what is happening? You can see there is this water which is now going on the undulating surface, and so here is a different slope, here is a different slope. So what happens? Slope varies, velocity varies, and all other parameters that we have studied in the morphology part varies. But when this same stream attains a graded profile, the second image you can observe, what happens? There is this smoothness in the curvature, isn't it? So what happens? This headwater carrying this particular sediment continues to flow in the same way till the mouth and carries that sediment A, which was here, in the same way to this part which is mouth. So this is where this profile of concave equilibrium is there. So there are four variables related to this concept of graded stream. So what is important here? Slope, discharge, channel characteristics, and sediment load. So now you know why we discuss this graded stream, because this is entire channel morphology part which is directly linked to the formation of this graded profile or the equilibrium profile of that stream. So in condition, the thalweg, this part, remember the deepest part of the longitudinal river profile, consists of a continuous concave curve, or the curves that just steep enough to transport all the material from one end to the other. So that is where it is important for a graded stream to have this entire smoothness, this profile of equilibrium. So if there are graphs given to you in the question that which of them represents a graded profile, remember this curvature. This kind of graph is what we represent a graded stream or graded profile or stream in equilibrium. That is important. So now, when we have studied in details the channel morphology, its various components, its various characteristics and important terminologies associated in it. So in the lectures to come, we are going to talk about applied geomorphology. So stay tuned, stay safe, and all the best wishes.